In the last video, I've talked about how we can use this force F equals to BIL to calculate the force on a current carrying conductor in a magnetic field. Here I want to consider how this force might be affected by the angle of the magnetic field. Now this formula actually assumes two things. I have mentioned one in the last two videos, and that is that the magnetic field has to be uniform, meaning that it has to have the same strength and direction over all of the currents that we want to calculate the force on. And in terms of field lines, it means that the field lines should be parallel and at equal spacings. And that's how we would represent a uniform field. Now the next condition for this, which I've not actually mentioned directly, but I've sort of assumed in the drawing, is that in order to use this formula, the direction of the magnetic field has to be perpendicular to the currents of the wire. They have to be at 90 degrees. Now, but what if it is not perpendicular? What if it is at an angle? Even if it is at 90 degrees, if the magnetic field is at 90 degrees to the currents, then we have seen that we understand from, say, the Fleming's left-hand law that the direction of the force should be perpendicular to both the currents and the magnetic field, right? The force is perpendicular to both currents and magnetic field. But how would this change how would all this change? How would the direction of the force and the strength of the force and the formula change if the angle between field and current is less than 90 degrees, for example? So let's take a look at what happens. Now, it would be easier if I just focus on the magnetic field. So suppose that I just focus on a small section of the wire, a small part of the wire, and on this small part of the wire there is this magnetic field acting downwards. There is this current going in this direction, and because of this there is a force going in this direction. Let me draw it in this order, so that there is a force acting in this direction when there is a current in this direction, and when there is a magnetic field in this direction. So in this situation, they are all at 90 degrees with each other. And I had that north pole there earlier on, up here, and directing the magnetic field downwards. Now, but imagine what would happen. What would happen if I put my north pole here? I put my magnet there instead, so that the magnetic field is along the direction of the wire. Or that's opposite direction. It doesn't really matter, but let me just say if I put the North Pole there instead, okay, if I put the North Pole here, then it would produce a magnetic field in the same direction as the current, parallel to the current. And what would happen to the force? That's a bit tricky to determine, but if the magnetic field is in the same direction as the current, then actually there would be no force. There would be no force. Okay. So let's see. Let me write down these results. If I'm talking about here the effect of the angle between the magnetic field and the currents. Okay, so let me summarize what I found just now. Now I'm going to just draw the magnetic field at a certain, let's say at a certain angle, theta, to the current. Now this field is still pointing in a downward direction. It's not very obvious from my drawing, but let's say it's still pointing in a downward direction, but it is slanted at an angle to the current. Now, so this angle, the angle between, let's say the angle between currents and field is theta, as I've labeled it. Now the force, the magnitude of the force, as we have seen two cases so far. One case was when the magnetic field is vertical, right? That when the field was vertical, that was what I talked about at the beginning. The field is perpendicular to the current, so the angle is 90 degrees. And we have seen earlier on that the force then is given by this formula, BIL. Remember that? And only just now I've described the situation where when the magnetic field is in the same direction as the current. So this means that the angle between field and current will be 0 if they're parallel. And I've said that the current, the force would be 0. The force would be 0 if current and field are parallel. Now, but what if it is not 90 or 0? What if it is, let's say, 70 degrees? Right, something in between. And what is the force then? There is a formula for this case, for the general case when the angle is not 90 degrees or 0 degrees. The formula is BIL times the sine of the angle. And this is the formula that we need to use if the angle is in between 90 degrees and 0 degrees. That means if it's neither perpendicular nor along the current direction, if it is at an angle. Okay, and in general, when that means if the angle is at some other value, if I just call it theta, then the formula would be BF equals to BIL times sine theta. Right? Whatever the theta is, we can just put in the angle here and calculate the sine of that. Now, and we can see that it agrees with these two cases because when theta is 90 degrees, sine theta is actually 1. Let me write out this separately. Sine of 90 degrees is actually 1, and sine of 0 degrees, right, 0 degrees here, is actually 0, which is why if I use the same formula with theta equal to 0 degrees down here, this formula would give me 0, whatever the values of b, I, or l, right? I will still get 0. Okay, so they agree. The formula agrees with my description here of the strength of F. Now, one more thing that I should mention. We're talking about force. So it is important to know a force. You need to know two things. You need to know the strength, of course, and you need to know its direction, since force is a vector. So if the next question then is, I still have the current in the same direction, but if the magnetic field is at an angle, at some other angle than 90 degrees, then what is the direction of the force? Would it still be in this direction? Okay, the rule here is this. If you have a force that comes from a current and a magnetic field, that force must always be perpendicular to both the current and the magnetic field. Okay, the force must always be at 90 degrees to the magnetic field direction, and the force must always be at 90 degrees to the current direction. So in this example, if the field at this angle is still along a vertical plane that contains this angle. Imagine a vertical plane around here that contains that this wire lies on. If the field is in this plane, then the force will continue to be perpendicular to the magnetic field because the force is perpendicular to this vertical plane that contains the wire. So in which case, as you change this angle, the force will still be in the same direction. But if you reduce the angle towards 0, this force will decrease. Eventually, when the angle is reduced to 0, the magnetic field would be along the same direction as the current, and the force should become 0. Okay, and in a way, it makes sense if you think in terms of the direction, because by the time the angle goes to 0, the magnetic field would be along the same direction as the current. Now, if both the field direction and the current direction are the same, then you would not be able to determine the direction of force of a force, because all we then know is that the force must be at 90 degrees to both the current and the field. But if the field is in the same direction as the current, then we just know that the force must be at 90 degrees to the wire. But if that's all we know, we don't really know the direction of the force, because I can have a force in another direction, vertical or opposite, and it would still be at 90 degrees to the wire. And the only way out is if the force becomes 0. Alright, so that kind of makes sense if you think in terms of the direction. Because if you have a current and a magnetic field in two different directions, and you say that the force is at right angles to these two directions, then we can actually determine a direction for the force. Alright, but if you just say that the force is at 90 degrees to just one direction, when both these and this are pointing along the same line, that actually cannot give us a unique direction of the force. But that would not be a problem if the force is actually 0.